Hello, greetings! In this screencast, I'm going to work through problem 2 from chapter 8. And so problem 2 is going to involve using tabulated PXY data to answer a series of questions. Okay. So the data below are for the system 1,4-dioxane methanol at 308.5 Kelvin. Right, so PXY, temperature is fixed. And then we're going to answer our series of questions. So the first thing I'm going to do is I'm going to go ahead and I'm going to sketch out my PXY phase diagram for an ideal system. And then that way I can look at the data in the context of my graph. And then I'm going to use that graph in terms of helping me to set up and solve my problems. Okay. All right. So remember, it doesn't matter how well you can draw your PXY phase diagram or how nice of a picture you can draw. My picture on my tablet is going to be even worse than my picture on the board. Okay, let's get that off. But I have pressure versus composition. I'm going to label my right axis, right? That's going to be pure component 1. My left axis will be pure component 2. When I'm plotting my PXY, temperature is fixed. So my left axis, I'll have P2 sat. And when I'm plotting with respect to the most volatile component, P1 sat is greater than P2 sat. So next I'm going to draw my bubble line, which is going to be a straight line between P2 sat and P1 sat. And then my dew line, I'll just draw on as a curve. Okay, again, it doesn't matter how great it is, right? This is a little overly curved here. But then high pressures are going to favor liquid, low pressures favor vapor. So line separating two phase, right? This is two phase. So line separating two phase from liquid. This is my bubble line, which I'll just label as bub. The line separating my vapor from my two phase, right? That's my dew line. Okay. Where my bubble line and dew line touch at my single point at my left axis, that's P2 sat. That corresponds to pure component 2. Right? For pure component 2, I transition directly from liquid to vapor or vapor to liquid at a single point. Right axis, this is pure component 1. And so in pure component system, I'm going to transition directly from liquid to vapor at a single point. Right? That's going to correspond to P1 sat. When I'm plotting with respect to the most volatile component, P1 sat's greater than P2 sat. Okay. All right, so now in terms of the data I have, okay, so we're given pressure versus composition. So if I were to plot this data, I'd plot X versus P and then Y versus P. Okay. So X1 equals Y1 equals 0, and this is P. Okay, this corresponds to what I would call P2 sat here. And then this would correspond to P1 sat down here. So now what we'll find, the way this data is tabulated is, well, P2 sat is actually greater than P1 sat. So the data is set up so that it's plotted with respect to the least volatile component. Okay, right. So this is pure component 1, is component 1's labeled. This is pure component 2, is component 2's labeled. Right, and we find that P2 sat or P1 sat is less than P2 sat, which tells me that what I'm calling P2, right, is actually P1. Okay, so my solution, okay, what I'm going to have to do when I actually plot my graph and try and quantize this is that, I need to switch the role of component 1 and 2. Right? I need to switch 1 and 2, right? So that 1 is the most volatile component. Okay, we could solve it the opposite way, right? In my picture, I would just get a mirror image, and I would just need to keep track of what I have. Okay, so now with that said, okay, so we're going to switch the role of 1 and 2. And so what I'll end up with is this will end up being P1 sat is 0.28. Okay, so when I switch them, that's going to be 0.28. And P2 sat will be this 0.081. And I have the data tabulated in MATLAB for when we get numerical answers, and so it'll be easy enough to switch. All right. So let's look at our first question then. So the first question is, what is the saturation pressure of methanol at 308.5 Kelvin? Well, in the problem's notation, methanol is component 2. So if I find pure component 2, right, which is this, then this would correspond to P2 sat, the corresponding saturation pressure, and it'd be 0.280 bars. Okay, so the saturation pressure of methanol is 0.28 bars. Okay, so the answer to A is, I'm just going to label this P sat of methanol is equal to 0.28 bars. Okay, and likewise the saturation pressure of dioxane is 0.081 bars. Okay. Cool. All right. So next, what is the phase of a mixture that contains 60% dioxane at 308.5 Kelvin? So that's just the temperature of my pxy and a pressure of 0.1 bar. All right, so dioxane mole frac is 0.6, and so that'd be 0.4 mole fracs of methanol. So I'm going to think in terms of methanol, because here in my plot, I have it plotted with respect to the most volatile component. Okay. So what I'm going to do is I'm going to draw on a line of constant composition. Okay, and so in this case, this would be Z1 equals 0.4. Okay, but the same strategy would be true in general. And the reference points that I'm going to be after is if I were to take this liquid mixture and I decrease the pressure, okay, where I hit my bubble line, right, that's called my bubble point. Okay, this would correspond to P bubs. And if I continue to decrease the pressure, where I hit my dew line, we call that P dew. Okay. All right, now at P bubs, right, so if I were to draw on my isobar for vapor liquid separation, right, what's key and unique is at my bubble point, then x1 is equal to z1, right, and we were calling this y1 max. And at my dew line, right, so this is where my picture's not great, I think my dew line's a little too curved, but at my dew point, then I have that y1, because I read y's from my dew line, is equal to z1, and that's where I would get what we were calling x1 min. So the key is in terms of determining what phase I have, is if I have a mixture of 0.4 mole fracs, is I want to determine P bubs, okay, and P dew. If my pressure is greater than P bubs, then I must be up here, I have a liquid. If my pressure is less than P dew, then I must be down here, I have a vapor. And if I'm in between, well, then I have a two-phase mixture. Okay. So now I'm working with Z1 is equal to 0.4, where I call that my most volatile component. When dealing with the tabulated data, right, I would actually need 1 minus this, right, which would be 0.6. Okay, and so what I need to find, okay, so we'll go over to MATLAB and we'll compute it, right, and hopefully make more sense. So what I need to find is that I need to find P bubs. So I'm looking for when x1 is equal to 0.4, right, I need to find the corresponding saturation pressure. And then I need to find when y1 is equal to 0.4, and I need to find the corresponding saturation pressure. Okay. Now in the tabulated data, it's going to be when x1 is equal to 0.6 and y1 is equal to 0.6 because it's 1 minus that. Okay, because the data is tabulated with respect to the least volatile component, right? But we'll work it all out in MATLAB, right? So 0.6, right? And again, 1 minus 0.6 is 0.4. Is going to be somewhere in between these 2 points. Okay, so P bubs is going to be somewhere around, I don't know, 0.22, let's call it, right? And I'm just going to sketch it on here, so I'll be able to check the reasonableness of this. So this should be somewhere about 0.22 bars. Okay, and then for P dew, I'm looking for when y1 is 0.6, because 1 minus that is 0.4, and that's going to happen somewhere around here. And so that's between 0.13 and 0.119. Let's call it 0.12. Okay. So it's going to be about right here, which is 0.12, right? And so key is, without even solving anything, without even actually computing the numbers, and we'll compute it, using the MATLAB code, is that P due, right, we know is going to be, P due is going to be somewhere between these 2 points, right? And both of them are greater than 0.1 bar. So without even solving anything, since we're told our system is going to be at 0.1 bar, that 0.1 bar is less than P due, right? So we're going to be down here in the vapor phase. Okay. So for B, I know we're going to be in the vapor. Okay. But we'll go ahead and we will compute P due and P bubs when we hop over to MATLAB. And then we can confirm, right, that 0.1 bar is less than P due. Okay. All right, but let's take a look at the rest of the problems. All right, and so then C is exactly the same, right? So C just builds upon it, actually. It's just asking for what the bubble and dew pressure of the mixture are, right? And again, we actually need that to solve B, right? So really B and C should probably be flipped. Okay, so let's go ahead and let's solve those two, and then we'll use that and we'll talk about plotting my data. Okay. All right, so I have an M file. So this is in MATLAB Online, and I tried to turn off my hotkeys in my screen recorder, so hopefully it works. And so this is just the data as provided. We're given P, we're given X1, and we're given Y1. And so what I'm going to do is I'm going to save as, okay, and I'm going to call this problem 2 solution. Okay. You should have access to this MATLAB drive folder, so this way you'll be able to see the original file if you want to try and solve it, and then mine. Okay. All right, so the first thing I'm going to do is, since we identified that what they're calling component 1 in the problem statement is actually my least volatile component, okay, I'm going to go ahead and I'm going to change 1 to 2. Right, and so all that is when I look at my problem, okay, we said that component 1, as they have it labeled here, right, must be the least volatile component, because this is P2 sat. Then in their notation, this is P1 sat. We get P1 sats less than P2 sat. So that tells me that the role of component 1 and 2 are flipped. Right? And so if I want component 1 to be the most volatile component, well, then all I would need to do is change this to 2. Right? I'd have to call this component 2. So in my MATLAB code, I'm just going to go ahead and change that to X2 and Y2. And then I would rather work with X1. So X1 is just going to be 1 minus X2. Good, my equal sign works, so I was able to eliminate my shortcut keys as compared to the last video. And Y1 is going to be 1 minus Y2. Okay, great. All right, so now let's think about what we need to do, right? So in the first case, we're looking for the bubble pressure and dew pressure when X1, right, is 0.4, right? X1 I'm calling methanol. And so what we said is, well, if I look at my X column, okay, and so I'm looking at 6, I need to find the value of P when X is equal to 0.6, which we'll do as 0.4. Okay, so to find P bubs is going to be interp 1. All right, and so now I always forget the order of things, so I'm going to type it in one here. All right, so if I can't remember what's X and Y, then I type it in here. So first is going to come my independent variable, my dependent variable, and then the where I want to estimate the value of my independent variable that I want to estimate my dependent variable at. So X, Y, then the X I want to use to estimate my value. Okay. So it's going to be X1, okay. Then my Y in this case is P, and I want to estimate it at, well, in the problem, we're looking at a mole frac of methanol of 0.4. So I type in 0.4, I run it, I get an answer of 0.2195. And so when I look at my problem, all right, 0.2195, right, seems reasonable right in between the two of them. Fantastic. Okay. Then we do the same thing with P due. Okay, so P due, it's going to be the same thing, interp 1. Okay, by default, it's just doing a linear interpolation. But now I'm going to estimate a value of P at a given value of Y. So it's going to be Y1, comma P. comma 0.4. Okay, so I'm looking for when y1 is equal to 0.4. Right, I run it, so now I get pbubs and I get pdo of 0.1248. 0.1248, right? We should be right in between those two. Seems reasonable. And so the key is, now I've got numerical values for pbubs and pdo. The pressure that we're given the problem is 0.1 bars. 0.1 is less than pdo, so I must have a vapor. And as a check of my answer, right, pbubs is greater than pdo, right, things are looking okay, and even just looking at the data, the values seem reasonable. All right, so we calculated pbubs and pdo. Cool, we have our reference points, and then the next thing we want to do, or we're asked to do, is just plot our data. So I'll generate a plot in MATLAB, and then we'll go ahead and we can talk on the screen if I were to print it out how I might label things. Okay, so now generating the plot, right? So actually I'm going to do two. I'll plot with respect to the least volatile component just so we can compare. So I'm going to plot x versus p and then y versus p. So I'm going to plot x1 versus p. And my bubble line I'll plot as a black line. And then I'm going to plot y1 versus p, and that's going to be a red line. My x label, I'll call it x1 or y1. My y label is going to be p, and I believe it's in bars. And that should do it. So if I plot this, I'm plotting with respect to my most volatile component. Bam, so here's pressure versus composition, x1 or y1. Here's my bubble line, right, and here's my dew line. Now if you look, right, we actually have curvature to our data, right, so our bubble line isn't straight, okay. Now that's okay, right, that's just a sign of this being a non-ideal system, right. The fact that I have curvature and it's positive, that's going to end up corresponding to positive deviations from Rayleigh's law, unfavorable interactions. But I draw an ideal, so the fact that I drew an ideal phase diagram, right, in my sketch, right, it doesn't matter, because regardless if it's ideal or non-ideal, how I'm going to set up the problem and think through the solution is going to be exactly the same. It does look like I have an azeotrope that's going to happen somewhere around here. Okay, but again, here's my PXY bubble line up top, dew line on the bottom, right? So if I were to draw in an isobar, my Y is greater than my X. This is a non-ideal system, right? But my solution would be exactly the same. So my solution, the sketch is just a guide to help me with my solution, right? And whether it's ideal or not wouldn't affect that. All right, and what I'm going to do is I want to, just for completeness, I want to look at what the figure would look like if we had plotted with respect to the least volatile component, right, which I'd call component 2. Okay, and I'm going to go ahead and I'm going to label this component 2 just so we don't confuse ourselves. But remember, if I plot with respect to the least volatile component, I'm just going to get the mirror image. So here's component 1, being the MVC, P1 sat's greater than P2 sat. And key is if I draw in an isobar, Y is greater than X, right? We plot with respect to the most volatile component, right? Because it's component 1, my most volatile component's what I'm trying to concentrate in the vapor phase. If I plotted with respect to the least volatile component, right, here I have what I would call P2, or component 2, P2 sat's greater than P1 sat. And if I draw my isobars, well, then I have X1 is greater than Y1, right? So it flips. Okay, so the role of the 2 flips. Okay, so I'm going to try and stick to MVC because that's standard convention, but it's easy enough to convert from one to the other. And for completeness, remember, in my head, high pressures favor liquids, so this would be my liquid phase up here. This would be vapor down here at low pressures. In between, would have two-phase. This black curve separating liquid from two-phase, that's my bubble line. This red curve separating two-phase from vapor, that's my dew line. Over here, this would correspond to pure component 2, so that'd be P2 sat, and this would be P1 sat up here. Okay, so hope that helps. If you have any questions, let me know.